is conducted by the Department of Chemistry, University of Colombo. We are Lakmara Rakubatta, Sanuri Gamanayaka and Gayatri Kaushalya, final year undergraduates at the Faculty of Science. Today, we have with us Dr. Ravi Mahajan, currently an Intel Fellow and the Director of Pathfinding for Assembly and Packaging Technologies for Future Silicon Nodes. He also represents Intel in academia through research advisory boards, conference leadership, and participation in various students' initiatives. He holds several patents in the area of microelectronics, packaging, most notably for the silicon bridge that has been foundational to Intel's EMIB, also known as Embedded Multi-Die Interconnect Bridge Technology.
Dr. Mahajan joined Intel in 1992 after earning a bachelor's degree from the University of Bombay in 1985, a master's degree from University of Houston in 1987, a Ph.D. from Lehigh University in 1992, all in mechanical engineering. Without further ado, let's welcome Dr. Ravi Mahajan. Good evening, Dr. Mahajan. It's truly a privilege and honor to be able to do this interview with you. Thank you very much for joining with us.
Thank you very much for having me.
To begin with, would you mind giving us a brief introduction about yourself, your childhood, and early education?
Sure. So let me start with my childhood. You know, if I look at my age, I suspect it happened a long time ago, but it's very fresh in my mind. I mean, I remember my childhood like it was yesterday. I am the middle son of three brothers. I was born in Mumbai, India. In those days, it was called Bombay, India. My mother was a high school teacher who became a high school principal, and my father was a engineer by background. We had, I think, a tremendous childhood in the sense it was extremely happy, a lot of fun, and my brothers to date remain to be my best friends. In addition to being, older and younger brothers, we still stay in touch. We are very well connected. I I went to a small school in Mumbai, but it was an excellent school in the sense the teachers were very caring. So I was lucky to be brought up in an environment where we had both emphasis on education and a focus on making sure that we were disciplined and worked hard. So that those sort of values were instilled in me when I was a child and continued with me. In India, as you probably know, you stay in high school up to 10th standard or 10th grade. Then you spend 2 years in junior college and then 4 years in undergraduate. So after my 10th grade, I joined Ruparel College in Mumbai. And then after that, I joined an engineering school. And in those days, depending on where your rank was, you had a choice of disciplines. So I picked mechanical engineering. And I graduated in 1985 with a bachelor's degree in mechanical engineering. I spent 6 months in IIT Mumbai doing an M.Tech or a master's degree. And then in January of 1986, I came to the United States, to University of Houston, where I studied experimental fracture mechanics under Professor Ravi who's a very well-known researcher in this area. And in 87, when I was finishing my master's, he offered me an opportunity to stay there, but he also said I should try out in other schools, which had, more distinguished researchers in the field. So in 87, I applied to and I joined Lehigh University. And I worked under Professor Fazil Erdogan, who people in the field of fracture mechanics know him as one of the legends in the field. I was very fortunate to get him as an advisor. So both my master's and my PhD, I had tremendous advisors. I changed my direction, as in I moved from experimental work to analytical work. And in 92, I finished my PhD at Lehigh. It was a fantastic time, 87 to 92. January of 92, I graduated out of Lehigh. Then I stayed at Lehigh for 4 months and joined Intel in 1992, May of 1992. So that's sort of my education in a capsule.
Could you please tell us what science means to you? What sparked your interest to get into the field of science? And how did you end up in mechanical engineering?
Ah, okay. So, I have to tell you that my views on science have evolved over time. Like most students, I also thought science was a way of logically constructing and finding sort of facts, and that was my thought process. When I was at University of Houston, I had an opportunity to take a course in technology and the philosophy of technology. And there one of the reading requirements was all of us had to read a book called The Structure of Scientific Revolutions by Professor Thomas Kuhn. And I find it to be a tremendously inspirational book in the sense he explains the way technology evolves. At that point, I recognized or realized that science is a way of structured finding of facts and then coalescing the facts so that you create a theory to fit in or try and fit them in an existing theory and then evolve that theory as time goes by. So mechanical engineering is very good in the sense it is very hands-on. You get a direct understanding of what is happening. It is based on the concept of models. And you model something and then you validate it through experiments and you continue to evolve the models as you learn more and more and you make sure that the fits you create that validate or invalidate models are something you understand. And mechanical engineering, because it's such a physical science, it's such an all-encompassing science, and it has such tremendous breadth that you can really, really understand the field as you get involved in it. And while you are doing this, you understand the mathematical foundations and things of that nature. So it sort of all blends together. And as you study the subject, you begin to understand how things fit together, and you understand the underlying beauty of conceptualization, the underlying beauty of mathematics, the value of mathematics in driving some of this. And I've been very lucky in the sense I've had a chance to explore all these things as I move through.
What made you migrate from India to the USA and the challenges you faced in adapting the culture of the USA? What are the differences you have seen between Asian scientists and Western scientists, such as their education system and thinking patterns?
So what made me migrate? I was interested in doing applied research. And I felt that the opportunities in the US were tremendous. And one thing leads to another. So when I came to the US, I was interested in the field of fracture because when I was in my 6 month stint at IIT Mumbai, I had studied fracture a little bit. When I came to University of Houston, I got a chance to really grow on that. And Lehigh was an opportunity to do even more in that field. So I came in search of learning. I can tell you that in my entire career as a student, I never thought about taking a job in between. Like I had made up my mind I wanted to learn. Uh, there is positives in both the US system of education and the Indian system of education. The Indian system of education, the one that I grew up in, teaches you to memorize a lot of stuff. It builds your acuity, your ability to keep things in your head, which I found very useful. So I have many occasions where I understood what I had memorized much later. But because I had it in my memory, I was able to build mental constructs. When I came to the US, I found there is a lot of opportunity to try out things. Independence in thought is very much prized here. And if you work with the right people, and this continues in Intel, if you look at Intel, a lot of thinking goes on and you are allowed to think your way through. So you can take the discipline of the Eastern systems and with the opportunity for innovation in the Western systems and grow. Culturally, of course, tremendously different. As most of us know, the food we eat in India or in our parts of the world, very different than the food you get here. So it takes a while to get adjusted to. but I like the discipline, the opportunity, the chances to talk to people and sort of flourish in an intellectual environment. So to me, both environments are very good, and I was lucky to be in good parts of both. So
It's really interesting to know about that. What made you join the industry rather than joining academia?
a good question. I actually wanted to, both would have been fine with me, honestly. I would have, I think, enjoyed academia as well as, and even today, I find that when I am at Intel, I do work very closely with academic institutions. So I like both parts of it. I joined industry because at that time when I joined Intel, uh, the US was just coming out of a recession. A company like Intel in those days was really looking to launch itself from a medium-sized company to a large company, and we had really innovative leaders. Like we had Andy Grove, who was our CEO at that time. Gordon Moore was still active at Intel. So some really, and Dr. Sunlin Chow, who, if you look at the literature, you will find is a great thinker. And then people closer to my field, they were all sort of, it was a great environment. And, so I joined industry and I haven't regretted it a single day. I always think it was one of the best decisions I made to join Intel. And the environment here is, I've been at Intel now nearly 28 and a half years. And I can tell you, I enjoy every day. And I'm not saying that just to say it, I'm saying it because it is literally true that working at Intel is an absolute pleasure because you get a chance to talk to some of the smartest people on a regular basis.
Dr. Mahajan, now we are moving
Yes.
onwards to our next question, which is based on the EMIB technology. We would like to know what paved the way for your research on microelectronic packaging technologies and what silicon bridges are, and how it became the foundation for Intel's EMIB technology.
Let me start by explaining a basic concept. As you know, Intel has for nearly 50 plus years worked on Moore's law and continues to drive evolution of Moore's law. Silicon is the best platform when you take technologies that can be homogeneously integrated, as in technologies that can be built on the same piece of silicon. But there are some technologies that cannot easily be built and they are optimized on different silicon. So then the package is the next best platform when you take technologies that are different and try and stitch them. So essentially what a package does is it takes different IP or different functional ideas and connects them together on the package, and it connects them away from the package as well. So if you look at heterogeneity, the question is how do you make the best possible connections? And I was thinking about this many years ago, and I thought if you have a choice always of something called fast and narrow, which means few connections but signals move very fast, or wide and slow, which means you send signals at a lower speed but many lanes. Think of this like a freeway system, for instance. You could choose to make a freeway with many lanes but cars are regulated, or single lanes but you allow faster speeds. Conceptually the idea is similar. So I invented Emib because I was thinking about how to do it. I came to the idea that silicon can offer very high density connections. Then the question was, how can we develop connections only where you want? And that became the basis for this idea, high bandwidth, low power interconnects, connecting to provide die-to-die interconnects that start looking like on-die interconnects. And that was the basis. And then it evolved on how you implement it. When you embed it, it's called EMIB embedded. So it evolved. First a silicon kind of bridge, then an embedded silicon bridge. So that was the thought process behind how we worked on it. And I had the idea. I worked with a few people, and we proved it out in reality. And now it has blossomed into a fairly significant technology that allows you to do interconnects like this and allows you to do mix and match like Lego blocks.
That is really interesting. We were so curious about that. Um, your research work has also led to high performance, cost effective cooling solutions for high-end microprocessors and the proliferation of photomechanic techniques used for thermomechanical stress model validation. Would you mind briefly explain to us the research work related to this and the success story behind this?
I'll explain the photomechanics first and then the thermals. So photomechanics, as you know, is the use of optical techniques to understand or to measure certain things like displacements or movement. And in my graduate work, I had already started working on a technology called, I had seen people in my field work on a technology called Moray interferometry. When I joined Intel, I had a chance to collaborate with Professor Bongte Han, now at University of Maryland, to take the same ideas and to see if you could visualize displacement and from there calculate stress. So, the idea of using light or optical techniques to visualize how stressed certain parts are. And then we applied it to microelectronics. We reduced the size, we got better resolution. I worked with Professor Han to improve the resolution so we could measure tiny displacements. And so a lab was born. And in that lab, we tried to actually demonstrate it. Now, thermals is another area. So as you probably know, as performance increases, the amount of power put out by a microprocessor or any kind of semiconductor devices uh, oftentimes increases. So I was lucky enough to be given a chance to try and develop methods to cool this. So in 1993, 94, I started a group which was looking at how to develop these solutions. Uh, and so we got a collection of really, really good people, very capable of some very innovative ideas, and they started putting things together. We figured out how to cool things. At that time, as you probably remember, we only had desktops. We did not have laptops. They were just coming in. So we looked at how to use heat pipes, for instance, to cool things. We looked at how to change the airflow. And so a number of ideas were born. And, this is like a movement. When a few good people get together, they have a known problem and they know how to evolve. That's how this all worked out. So we developed a number of techniques which today are broadly proliferated. Lots of people use them in laptops and in others. And I was part of a very good group of engineers at Intel.
Doctor, could you please briefly tell us about the most challenging project that you have been involved in? And how did you manage it successfully?
Uh, yeah, I can tell you that we have had a few challenging projects in the mid and early 90s. We were asked to cool the Itanium class of processors. In that time, the power dissipated by some processors was in the 4-5 watts. This processor was 50 to 100 watts. So you can think about both the perception as well as the reality and the challenges of doing it. The best way to solve problems, I think, is to get the best group of people together and make sure that you give them the empowerment to do something, give them the facilities to do something, and work with them. So I was lucky enough to work with good people. I was lucky enough that I had managers who allowed us to work on some of these things. And then the second project, I think, is this concept of EMIB is something we took from concept to production by building it. And doing that, we learned a number of things along the way. Uh, it was excellent teamwork. And Intel, one of the good things about Intel is that you get really good engineers who collaborate very, very effectively and somewhat informally, in the sense you can move very fast because the communications are very good. So I think a combination of good teamwork, managers who remove roadblocks, and excellent engineers to begin with. I think those, so in some ways I was lucky that I had such good collaborators.
Dr. Mahajan, you have worked as a group manager of a team responsible for thermal and mechanical solution, tool, as well as analytics. What are the challenges you have faced when managing a team, and what qualities a person should have to be a good team leader?
So I had two roles. One was a manager, and I also was a technical leader for a lot of these people. So it was a combination. As manager, my own managers taught me that the thing you can do as a manager is to look at what prevents your employees to work, or people who work in your groups, what prevents them from being successful, and remove their roadblocks. And this was something I was taught and which I tried to teach my successors. So I did this. The other thing is you look for the best talent, as in you look for people who can work very well with effectively with teams, and then you create the right structures for their teams. So as a manager, that was my strategy, to reduce the amount of roadblocks, or minimum, or get rid of roadblocks, eliminate them. As a team leader, my objective was to collectively decide what we were going to do, put some really challenging goals outside, and then figure out how to get to them. And I have found that engineers are extremely innovative in the way they think, as long as they know that they have a chance to succeed and they have somebody helping them move forward. So in that sense, the challenges always are finding out what exactly impedes their progress and then to minimize it.
Dr. Mahajan, as we got to know, you have won many awards, including Interpac Achievement Award, Mahbub Khan Outstanding Industry Relation Award, and Alan Cruz Thermal Management Medal. What was the secret behind these achievements?
Good question. Probably right place at the right time. I joined Intel at a time when, as I said, we were expanding. We had many opportunities. Uh, I guess the primary secret is that I had managers and thought leaders at Intel who both trusted me and gave me the opportunity to move ahead. Because they opened doors, I had a chance to do more things. Uh, I can name a few, but there are many more. My first manager, Mustafa Agazadeh, who is now the vice president at Intel, one of the most brilliant minds and most dedicated sort of focused person. I had a person called Bala Natarajan, who was a friend as well as a manager. Dr. Nasser Grayeli, who led our organization, a tremendous mentor. Bob Sankman, Intel fellow who has now retired. Uh, and I currently work with Ram Vishwanath, who's a brilliant engineer also. So I was very lucky to get great managers who gave me a chance. I ascribe a lot of my success to uh, their backing me, offering me a chance to move. In my mind, that is the reason for this.
Let's move back to Intel's EMIB technology. You hold more than 40 patents, including the original patents for silicon bridges that became the foundation for Intel's EMIB technology. How did you manage to do such innovative projects? What is your advice for a young scientist on how to build up the thinking pattern to become innovative?
The first, I think, is I'd say two things. One is describe the problem you want to solve very, very carefully. You will find that the problem you have to solve is sometimes difficult. Like if you crisply find out the question you are trying to answer and write the question you are trying to answer, that is, in my mind, the first step. After that, you can come up with various ways of doing it once it is clear in your mind what you are trying to solve. So in my mind, once the problem statements get clear, then you can come up with a number of ideas, and these ideas, if they are implementable and if somebody says are worthy of a patent, then you go for it. But the trick is to define the problem correctly and then come up with ways to solve it. And you will notice that engineers in general tend to be very innovative once they have an understanding of what they are going after. And if they have the right resources, you can definitely succeed. So defining the problem to me is half the battle already.
Other than solid state and thermal related studies, Dr. Mahajan, is there any other field that you have been involved in?
Um, I won't claim to have expertise, but I have looked at materials and the evolution of materials and how they can be used for different applications. I have looked at modeling technologies, and how to model things. I have been part of research activities where we look at things of this kind. We are looking at different ways of doing communication. So these are, and then system definitions. I also have had a opportunity to look at things like wearable electronics and medical devices. Even though I don't have direct influence on this, I am part of the IEEE Heterogeneous Integration Roadmap. And when I'm there, you get a chance to listen to a number of people in these fields. So you get a interest in this. And I have a little bit of interest in applied mathematics as well. So.
In your point of view, what will be the future of this field? What are the possible research areas and opportunities that the budding scientist can work on?
So let me talk about packaging. As I said, heterogeneous integration is complementary to homogeneous integration. The role of a packaging engineer is to deliver interconnect technologies that are capable of offering high bandwidth, low power interconnect. If you look at the roadmap that we have presented, we are just in the first or second generation. We can project about 6 to 7 generations. And if the width of this generation is 2 to 3 years, if you say you have 5 more generations, we are talking about 15 or 20 years more of just pure definition of interconnect. After that, there is architectures, like how can you take these interconnects and stitch these things differently? That's another. Coming up with innovative cooling methods is a third area of focus. Coming up with smart ways of delivering power, which is low parasitic, as in low loss, is another area. Collaborating with circuit designers to come up with high bandwidth, low power interconnect is another great area. Systems are going to evolve. Different ways of stitching systems is going to be important in the future. If you believe that the future is a world of data, and data is sort of the, enabling data is where the future lies. And you can see the difference. If you just compare life 10 years ago to life today, you will notice that you have access to so many things. For instance, we are talking on a Zoom link right now. I bet you could not have imagined a Zoom link 10 years ago, where you could have such crisp communication. If you extrapolate this, or you've seen things like WhatsApp and things of that nature. So data and enabling data. And the packaging engineers are a big part of enabling or creating the infrastructure for the transmission of data. So, heterogeneous integration, if you just look at the roadmap, there are so many areas where engineers can work. And I think that there is a tremendous opportunity in all of these, and in underlying sciences like material science and materials for some of these problems, modeling for some of these problems, tremendous opportunity.
So what are the challenges up ahead in the industry and to the students who wish to join corporations like yours?
Opportunities are, there are many. You can, if you just look at the field of packaging, as I said, you could look at interconnect scaling, high-speed I/O. You can look at signaling. You can look at collaborations of creating interconnected systems. There is a tremendous amount of opportunity in all these areas. And if you are a young engineer, and if you work in my field, which I'm very passionate about, it's a multidisciplinary field: material science, mechanical engineers, electrical engineers, process engineering, chemical engineers, all kinds of opportunities in all of this, and because it's both a technically challenging field that is economically circumscribed, you have a chance to do a lot. Like I am personally extremely bullish about the fact that the fields of packaging or semiconductor engineering, or in general the field of microelectronics, have so many things to work on. We have engineers who are process engineers who focus on improving processes, who look at new materials. So there's a whole host variety of opportunities to work in this field.
From your experience as a leading scientist, what advice would you like to convey to the young scientists or students who are aspiring to do well in science?
As a young scientist, my advice would be that there's two parts. I think if you notice, a lot of engineers are very, very good at analysis. They are able to
process information, analyze information in a very disciplined fashion. I think if we complement it with developing ideas, as in if we focus on coming up with new ideas by which problems can be solved, focus on new technologies. I personally believe the future is very bright. Analysis is something we learn during our engineering educations, during our general education. We learn how to deconstruct a problem and how to analyze it and improve it. If we can figure out new ways of solving the same problem, if we introduce innovation in our thought process, like a desire to find newer ways of doing it, I would highly encourage all students to look at the same problem or to look at new problems and come up with different ways by which you can solve it. That, in my mind, is probably the key. Ways to solve new or existing problems in a different manner. To always adopt a very sort of can-do attitude and try to solve problems. That, to me, is the right way to do things.
As our final question, what is your proudest moment as a scientist? And to anyone who is starting now, how would you advise them to stay strong in the face of trial and tribulations?
Okay, I was thinking about this question that you asked. To be honest, my personal proudest moment was in high school when I got my first award, and I was in the presence of my parents. I got to receive the award. As a scientist, some of my proudest moments, there is quite a few. One of the moments which I was very proud of is the day I was told I was an Intel fellow. It was January 4th, 2017. I got a phone call that said I was an Intel fellow, and becoming an Intel fellow is an honor. I was very, very, very happy that I managed to achieve this milestone. I was also very happy the day I became IEEE fellow. I felt that it was good recognition. So to me as a person, it felt very good. And similarly, when technologies that you work on succeed, it's always nice to see technologies that you work on actually come to fruition. So there's not one single moment, but there are many of these that you can pinpoint to. So the day we decided that we were going to move forward with Emib was another proud day. The day we saw some of the processors we had worked on actually make it into production and they're announced was a proud day. So there are many.
Before we wrap things up, is there anything else that you would like to add, Dr. Mahajan?
First of all, thank you for the opportunity. I don't have much advice except to point out that there's a few things you could think about as you move forward in your careers. One is look at clarity of communication, look at building bridges, being able to create networks of people, because I have found creating networks and leveraging diversity of thought, talking to different people and looking at how they look at a problem is a very, very good way. So I have always, and one of my bosses, Bob Sankman, always pointed this out to me, that listen to different viewpoints. Don't jump into solving a problem because you think you know. Oftentimes, engineers of my generation seem to know what to do. I am not sure they're always right. So it's always useful to listen to diverse viewpoints, and it is always very important to respect diverse viewpoints and then communicate very effectively. Like when I present, I try to tell a story that somebody is interested in. So those few tips, I suspect are, at least that's what I have learned, and hopefully they're useful to somebody.
We are truly grateful for the amazing time spent with you. Thank you, Dr. Mahajan, for spending your precious time and sharing your valuable ideas and knowledge with us. We wish you all the best in all your future endeavors. Have a great day.
Thank you. Thank you. Thank you for the opportunity, and all the best to all of you, and Happy New Year.